We'll speak about iRRAM for nodes. Thank you.
Yes. Okay, so let's start on the talk, shall we? Okay, so today I'm going to present about iRRAM for nodes. So basically, the skeleton for this talk will be about the introduction first, about what I've done and what the work is about, and then we'll go over some basics about knot theory, and then the specific test that I've done in the knot theory called Burrell spectral test, and also the use of exact real computation in this work, and explain about what exact real computation is and what iRRAM is, and finally we'll go over what I've done in the implementation part, which is the problem itself and the implementation. Okay, so let's get into the intro. So first, the motivation behind iRRAM for knots is that in knot theory, usually it is a discrete problem, but in some cases there could be problem involving real numbers and continuous problems, and which is hard to prove and also require tedious proof methods, which in this case computer assisted proof is comes very helpful in proving some theorems and also finding some complicated knots in knot theory. So to use this computer to assist our proof and using the theorem in real numbers, sometimes we can use floating point models of computation, but that model can be imprecise in some cases because the floating point model also have limited precision, and sometimes the floating point model can incur error propagation, in which sometimes the error in the cases is not noticeable in the beginning, but it accumulates over time when you tested the theorem over and over again, and the process becomes longer and longer. The error becomes hard to notice and hard to debug for the programmers. Okay, so for the formulation of the problem, what the main problem is to decide whether a given braid is reducible or exchangeable. The keyword here is the braid and reducible and exchangeable, which I'll explain in a little bit. So what is a braid exactly? So the braid is defined by using the braid groups, which is the group called using Artin generators. The standard Artin generator can represent the braid using these braid relations. So at first, the braid relation is the braid group on n strand is denoted by Bn, and then there are n-1 generators, which can be seen here, where the crossings over the right over left is considered the sigma I, and then sigma I inverse is the left to right crossings. So usually the braid is oriented down, but sometimes it can be oriented up. It is denoted by the arrow. So if the braid is down like this, I'll only draw 3. So this is braid 3, and the braid relation represents what equivalence of the braid can show us. So the first one is the commutation of the braid. So if the braid is different by more than 1, so I'll draw braid 4. Okay, so if you commutate the braid, so if basically it says that if you do the braid swap of the groups that is larger than 1, because this is sigma 1, sigma 2 crossing, and sigma 3 crossing. If the braid is larger than 1, then it doesn't really matter the order they represent. So if you do, in this example, sigma 1 and then sigma 3, and then you undo sigma 1 and then you undo sigma 3, then basically it represents the same braid. So you right over left and then left over right like this. And then this one also like this. So basically you can see that the braid will undo itself both ways. So it generalizes to all the end strand braids in this case. And also the second one is when the sigma is next to each other, then you can swap Jij and then Iji is equivalent. So basically it looks like this. So I'll draw it on that side. So here the braid is like this. And so this is sigma 1, and then this is sigma 2, and then you do sigma 1 again. So this is sigma 1, sigma 2, sigma 1. And then if you follow the relation, then it is equivalent to sigma 2, sigma 1, sigma 2, which is like this. So if you look at this, you basically if you move this crossing over to the bottom and the two braids are equivalent. So this is the basic of art generators. And then every knot and link is the closure of the braid. So using the braids, it is very useful to solve the knot and link categorization problem. So the closure of the braid is as follows as in the picture. So you connect the braids like this. So this is called closure, and you can see that it is a knot, and it can be knot and link. So the last sentence says it is called Alexander's theorem. So every knot and link that can be represented, it is the closure of the braid. So yeah, you can categorize every knot and every link using the braid. So to study about knot theory, you can use braids as an intermediary to categorize it. So next is the Burrell representation. So the Burrell representation is the matrices in the form of the representation, which can represent the braids using the iRRAM generators. Because if you look at how you transform the braids using Burrell representation, it has the exact same properties as the braid relations that I have mentioned before. So here the matrix denotes the form of the matrix representation. So for example, sigma 2 can be represented using the identity matrix and then blocked with that form of the matrix, and then blocked again with another identity form, identity matrix. So the matrix will look something like this, and then have the t, the 1 0 0 t minus t 1, and then 0 0 1 like this, and then 1 all the way down, and then 0 here, 0 here. So if you multiply it together, you can see that it have the same properties as the iRRAM generators. And for the inverse, you just take the inverse of this matrix. So it's gonna be something like minus t inverse here. I'm not sure, something like that. But basically, the form of the matrix is the general linear group of the dt and t inverse. So if you multiply it together, you get some polynomial of t and t inverse. So it's some kind of Lorentz polynomial, such as like if you multiply together, you can get matrix like t squared minus t here, and then t plus 1 over t, and then 1 here, something like that. It the representation of the braid can be mapped onto a matrix, which is useful in transferring the braids from discrete to some kind of continuous problem. Okay, so for the conditions of the braid, the first one is reducibility, where the theorem says that the closure of the braid is related if and only if there are three moves that can be done that is related the two braids together. The first move is the conjugacy. So you do the first move and then you undo the first move that you've done. So the braid closure is related because if you close the braids and you have some kind of move here called alpha, and then you have the move here called alpha inverse. If you close up the braids, then alpha and alpha inverse cancels out and you get the same braid closure. The second and third one is the braid stabilization and destabilization. So here the picture is the stabilization, and from this side to this side is called stabilization, and you go back is the destabilization. So basically the braid first has three strands, right? So if you add another strand and then you cross it over, it's called stabilization. And then if you undo the crossing and then remove the strand, it is destabilization. So, and if you close up the strands together, you can see that you can remove the last strand out, and it's basically an unlinked. So it can make the same knot and the same link. So this is useful because if the braid is related like this, then it represents the same knot and same link, which can be used to categorize knots and links in the knot theory. Next is exchangeability. So the braid is exchangeable if you can do the exchange move. The exchange move is first the braid has to be in this form. Alpha is some braid from 1 to n-1, and beta is some braids from 2 to the second strand to the nth strand. So, and the n has to be more than 4. So if the braid is in this form, and then you can do the exchange move, then the braid is exchangeable. So what is the exchange move? So the definition looks quite complicated, but basically it is you do the full twist first after alpha, and then you undo the twist after beta. And this is called exchangeability. And basically it also tells us that the braid is equivalent if it can if it admits the exchange move. So these two properties, reducibility and exchangeability, have been proven by one of the supervisors, Professor Alexander Stoyanov, that using the Burrell representation, the matrices have these eigenvalues in which if the eigenvalue is not equal to 1 and the braid is some conjugate, which means that the braid is reducible, then all of its eigenvalues is in some certain zone, which is where the lambda denotes the eigenvalue and S gamma is some conditions, some equations below. And the exchangeability is also related on the inequalities that is shown below. So what does the inequality look like? So the inequality looks like this. So the reducibility will, going back to the equation, you can see that it is some absolute, which the center of the circle is f to the n over gamma, and the radius is 1 over gamma squared minus 1. And it forms a circle like this. So if the, let me, so you, if the circle is here and the braid is reducible, then all of its eigenvalue will always be in here. And also the unit circle. So if the braid is not in the unit circle, then it must be in this. So the zone of the eigenvalues will be this union with the ring here. And same for exchangeability, where the exchangeability change the zone from this into the Descartes oval. So the Descartes oval is as in the picture. So it is the ring union with the Descartes oval, some kind of oval like this. And as you can see, the zone here is closed, which is because the equation here is less than and equal to, which is admits the closeness of the region in the complex plane. So if the conditions or the obstruction here is if you find some eigenvalue that is outside of this zone, the closed space here, it creates an obstruction, which tells us that the braid is irreducible, or in the second case, the braid is not unexchangeable, in which if the braid is irreducible and unexchangeable, then it communicates to us that the knot that is formed by the braid closure is some fundamental knot that cannot be undone in some cases. Okay, so to recap, the motivation using the exact real computation here is that the real testing of these zones of the eigenvalue in here is needs to be used using the real computation, because one of the theorems says that the eigenvalue can be dense in the given region. So if some precision is only fixed, then there could be some eigenvalues in which is in the zone, but the precision does not reach the full the full test that it is in the zone. So you cannot find the obstruction of that braid, in which iRRAM comes in and solve here. So the exact real computation here is is calculates real number using solution that is dynamically determine the precision. So in the floating point case, the real computation is fixed, but in the case of iRRAM, the point of the real number will dynamically determines the precision that is needed to determine that this point is in the zone or not. And then it keeps recomputing until the eigenvalue is determined that it is outside or inside or on the boundary of the zone. So the exact real computation that I've used the library is the Professor Norbert Müller's iRRAM, which is C++ implementation of the exact real computation. And in this case of the knot theory computation, it is a decision problem in which it decides whether the braid is reducible or non-exchangeable. And for decision problem, the Kleinian value is used, which is it lazily determines the conditions whether it is true, false, or unknown, and then it keeps the value until the point is known. Point is known, that is outside or inside or inside the zone. If it is unknown, then it is recompute until the eigenvalue is determined. And by finding the eigenvalues, we can use root computation as intermediary step to compute, turning the matrix into the characteristic polynomial, and then use the root computation, which is provided by Sewan-Spot implementation of graph iteration in iRRAM X, which is an extended part of iRRAM that Sewan-Spot have implemented. So the root of the polynomial can be found by using the technical graph iteration, which is at first the root of polynomial is unknown, right? So basically the characteristic polynomial is given, and then the graph iteration iterates on the complex plane, in which it closes in on the roots of the polynomial, the characteristic polynomial. For example, if the degree is 3, maybe the graph iteration can provide some zone of the eigenvalues, like some kind like this. And then if you find that this is the unit circle and this is this, if the eigenvalue is overlap with the disk, it recomputes until it finds that the eigenvalue is in the disk or is outside the disk. If the iteration finds that the eigenvalue is outside the disk, then it returns that the rate is irreducible, or in the other case it's non-exchangeable. Okay, so to recap on the motivation, the representation of the matrix is the real number and also complex real number. So with unlimited precision, in which floating point numbers does not suffice, and so the theorem needs exact real computation to compute whether the given rate is reducible or unexchangeable. And also the theorems of the computable analysis said that if the topologically test region is open, then this test is semi-decidable. So as I said before, the test region of the obstruction is closed, right? So if you find some point in the complement of the test region, then you can know that it is irreducible. So the complement of the closed region is open. So you know that by theory that it is semi-decidable. Okay, so let's go on to the implementation outline. So to the rate first, right, is given using the Artin generators, and then the program converts the Artin generators to its Borel representation, which is the matrix that I've shown before, and then it computes the characteristic polynomial such that using the basic using the algorithm called Fourier method to turn the matrix from its Breuer form into the characteristic polynomial, in which at first the characteristic polynomial is in some form of the polynomial of t, like in some cases I'll show the example. So it can be like t squared plus t minus 1 of lambda squared plus t plus 1 lambda plus some constant 1. It will be in this form where the coefficients is the polynomials of t, and then we iterate through the t's such that the t is substituted and create the characteristic polynomial. So going back to the equation, when you substituted the t in here, so the gamma and alpha is gamma, alpha, and s is some kind of substitution of t, in which the t is on the ring, where t here is the norm of t is 1. So if the t is substituted, you can see that the eigenvalue is, you can test that the eigenvalue is in the zone or not. So we iterate through the t's in which the t is on the ring, and then you lazily find the Boolean expression of each t, and then you combine it to test the eigenvalues if any one of the t's is in the test region of the ring, or in the exchangeable case is in the Descartes oval or not. You can find the implementation of the code on my GitHub, and also the implementation is in C++ in iRRAM, in which the iRRAM works by using the combining all the lazy Boolean expression first, and then test the eigenvalues. So in iRRAM, you need to provide the expression before you can test the values. So in theory, the infinite number of t's can be tested and is still semi-decidable, but the iRRAM library does not provide the necessary tools. So in the way of programming iRRAM, you need to find all the expression first and then test it later. So in my cases, you need to provide some bound of t to test the eigenvalues. So only the finite number of t's can be tested. Okay, so let's go on to some challenges and limitations of this program. So first challenge is that iRRAM is hard to install, which I provide some guidelines on installing iRRAM in the GitHub, and also when after installing iRRAM is also have some different approach in programming, which is not like imperative in some cases. So you need to know the ins and outs of iRRAM before you program this thing. And also the semi-decidable nature of the problem does not guarantee that the program will halt in the case that the break is reducible. And in some cases, if the break is irreducible, there can be irreducible breaks such that there's no obstruction, because the theorem only says that if the break is reducible, then all of the eigenvalues is in the zone. But if the break is irreducible, then there can be no obstruction. But in some cases there is an obstruction. So it is useful in the cases where you need to find just one or some cases of irreducible breaks, or in the other non-extensible breaks. And also the other limitation of this program is the runtime of the root finding algorithm, which is long, using the characteristic polynomial and then the graph iterations on every possible t that you could put inside of the matrix. So to circumvent this, there is also another program in the GitHub, which is some soft test, where the test is up to only some up to the precision that you are required, in which the obstruction can be found, but the it does not guarantee that if the obstruction is close to the disk, then it will find the obstruction. But if the obstruction is far within some p that you have given, then you can find it. It is improvement in the runtime, where you can find some the break that is irreducible with the obstruction that is not precise enough, but the program does not find the obstruction in all of the cases where the braid has an obstruction. And also, there's also, you can find the eigenvalues using QR algorithm, but it is not stable enough, but maybe the runtime might be better, but it is not stable. So for me personally, I haven't tried using the QR algorithm instead of the using characteristic polynomial, but to compare the stability and compare the performance. But in this case, it is a proof of concept that using the root computation to find the obstruction works to find the irreducible and non-extensible breaks. Okay, so that's it for my presentation. I would like to thank my supervisors, Martin Ziegler and Professor Alexander Stoyanov, and the library that I've used for C1 and Norbert Müller, iRRAM and iRRAM-X. Thank you for listening.